In this video we will take a look at entropy. Entropy is a little bit of a difficult concept to deal with at the non-calculus base level and even the calculus base level because it really requires more mathematics. But the concept of entropy is simple enough. Entropy is a state variable. That is, it is something that defines the state of the system, and it measures the number of ways that a microscopic system can be arranged. Think about this, think about if you were dropping some coins. And if you try to drop the coins one way, say you drop 4 coins, one possibility is that the 4 coins would happen to land on the table exactly on top of each other. And there are different numbers that you could do this. So you could put 4 different ways that you could put this one down. And then once you put that one, there'd be 3 ways you could do the second coin, 2 ways the first, and 1 way the second, neglecting the heads or tails. So 4 times 3 times 2 times 1 is the total number of different ways that you could arrange the coins so that they landed straight in this configuration. And that seems like quite a lot. 4 times 3 is 12, times 2 is 24. So there are 24 ways. If you take each different possible way of doing the heads, you have to multiply that by another 2. So many ways, 24. But there are a huge number of ways that the coins could fall on the table and not land on each other. They could land here, or instead they could land maybe like this. And because nature is so democratic, each possible way it can happen, each microstate that we have, is equally probable. So to determine what's called a macroscopic state, the things that we see here, because we don't see the individual atoms, you have to count up all the different ways something can happen. And the more ways something can happen, the more likely it is that that's what will happen. So what happens when you drop coins is they land in various configurations like this. They don't land like that. And it's sometimes said that nature tends to disorder. I don't kind of really like that statement because it makes it sound like it prefers something special about these states. It doesn't prefer the fact any one state specially. There are just a lot more ways that you can drop coins and have them fall randomly disorganized than there is a way to fall in a nice stack. So nature tends to go to the way that is most likely, has the most different ways to do it. But each individual process is equally likely. Now, this should say coins here. We can actually measure that. It's not easy to do that. If you could measure up all those different ways to do, you could say that the entropy is defined as K times the natural log of omega, and omega is the number of ways the state can be arranged. And K is the Boltzmann constant. Now it turns out that that's not what we tend to do. What we tend to do in this course is to calculate entropy for constant temperature problems. So a change in entropy occurs whenever heat is added to a system and for constant temperature, which is the only thing we'll consider, you can calculate the change in entropy as equal to the heat divided by T. Again, this only works for constant temperature, but that's all we'll be considering. So if you add heat to a system, then you also can think of it as adding entropy. Now here's the thing, the amount of entropy is dependent on whether you add it at a high temperature or at a low temperature. So you can add more heat at a high temperature and have the same change as entropy as you can, for instance, to lose a change of entropy by dropping less heat at a lower temperature. This is very important in the Carnot cycle. In the Carnot cycle, you bring in more heat, Q, at the high temperature, But the change in S at the high temperature is exactly equal to the loss of S at the low temperature when you have a negative Q, but you do it at a lower T. Now, let's go one step further. The second law of thermodynamics. The second law of thermodynamics states the following: the change in the total entropy of a system and its environment will occur in such a way that it is greater or equal to zero. So over a total process, delta S, which is the change in S of the system plus the change in the entropy of the environment, will always be greater or equal to zero. What this says is that on their own, processes have a direction that they want to follow. Now, people have always known this. If you drop a glass, it breaks, but a broken glass doesn't spontaneously jump up off the floor and reconfigure itself. There is a natural direction to the time of the flow of the universe, and this is what the second law of thermodynamics says. Now, the most efficient heat engine we have is a heat engine with no change in entropy, the Carnot cycle. And using our requirement up here about Q, let's put that into this equation here, and we see that the efficiency, we said earlier, was QH minus QC over QH. This would be the change in the entropy times TH minus the change in the entropy times TC over the change in the entropy times TH. But in our case, the entropy change was the same. And so if we can assume the Carnot cycle where that's the case, then we find that the efficiency is simply TH minus TC over TH. I'm sorry, I don't know why I had a C there. Or 1 minus TC over TH. If you could drop the heat to a reservoir that was at absolute 0 Kelvin, you could have a 100% efficient engine. But because the environment that you're dumping it to is not going to be at absolute 0 Kelvin, there will always be some lost efficiency. What you can do is try to make this temperature difference as large as possible. So for instance, if you have a nuclear power plant, let's say Comanche Peak, you have some hot reservoir and you have water or other fluids going along, going through a generator, creating electricity, and then that water has to be cooled, and it's cooled by another circuit that goes and flows water back to Squaw Creek Reservoir, which is TC. The difference between these two, if it was a perfectly efficient Carnot cycle, would give you the maximum efficiency by which we could get the energy out. Some of the energy that we've generated from the heat is always going to be lost into the reservoir of the lake and not into the useful work of turning the turbines, which then turns the magnet, which generates electricity. There's no such thing as being 100% efficient in any type of heat engine. All right, that finishes this discussion on entropy.